In this video, we will talk about sampling distributions of a sample mean. By the end of this lesson, I hope that you will be able to calculate the mean and standard deviation of the sampling distribution of a sample mean, x bar, and interpret the standard deviation. I hope that you'll be able to explain how the shape of the sampling distribution of x bar is affected by the shape of the population distribution and the sample size. And finally, if appropriate, use a normal distribution to calculate probabilities involving x bar. Sample proportions usually arise when we are interested in categorical variables, like what proportion of US adults has watched Survivor, or what percent of the adult population attended church last week. But when we analyze quantitative variables like household income, lifetime of car brake pads, blood pressure, etc., we are interested in things like the mean, median, or standard deviation of the variable. The sample mean, x bar, is the most common statistic computed from quantitative data. The sampling distribution of the sample mean, x bar, describes the distribution of values taken by the sample mean, x bar, in all possible samples of the same size from the same population. Here are two approximate sampling distributions of the sample mean year of pennies for samples of size n equals 5 and n equals 20 from a theoretical population of 2,000 pennies. Notice that their shapes and variability, in other words, standard deviation, are different, even though their centers are approximately the same. Suppose that x bar is the mean of an SRS of size n drawn from a large population of size big N with a mean mu and a standard deviation sigma. Then the mean of the sampling distribution of x bar is the mean of the population. So mu x bar equals mu. Therefore, x bar is an unbiased estimator of the mean for the population. The standard deviation of the sampling distribution of x bar is approximately the standard deviation of the population divided by the square root of n, your sample size. And this is true as long as the 10% condition is satisfied. In other words, your sample is smaller than 10% of the population. If you don't meet the 10% condition, the actual standard deviation of the sampling distribution is smaller than the value given by the formula. This is beyond the scope of this course, however. The formulas that you see here are on the formula sheet that the College Board will give you on the exam and that you may use anytime you would like in this course. If you're curious as to where they come from, you can check page 504 in your textbook and they show you how they're derived. The standard deviation, as you might expect, measures the typical distance between a sample mean, x bar, and the population mean, mu. The variability of the sample mean depends on both the variability of the population, sigma, and the sample size, n. Values for x bar will be more variable for populations that are more variable. That just makes sense. And values of x bar will be less variable for larger samples. Specifically, multiplying the sample size by some number a will divide the standard deviation by the square root of a. If you're asked to interpret the standard deviation, this is what you can say. In SRSs of size whatever n is, the sample mean of whatever x bar represents will typically vary by about whatever the standard deviation for the sampling distribution is, units from the true mean, mu, and don't forget the units. Now, notation matters, and you'll notice there are a lot of symbols you've learned in this course so far. We've got p hat, x bar, n, p, mu, sigma, the mean for the p hats, the sigma for the p hats, the mean for the x bars, the sigma for the x bars. They all have specific and different meanings. So either use the notation correctly or don't use it at all. If you use it incorrectly, you can expect that you will lose points on the AP exam, and therefore I am going to be picky about how you use your notation. All right, so let's look at an example. A grinding machine in an auto parts plant prepares axles with a target diameter of a mean of 40.125 millimeters. The machine has some variability, so the standard deviation of the diameters is sigma, 0.002 millimeters. The machine operator inspects a random sample of 4 axles each hour for quality control purposes and records the sample mean diameter, x bar. Let's assume the machine is working correctly. So first, identify the mean of the sampling distribution of x bar, and then calculate and interpret the standard deviation of the sampling distribution of x bar. And in order to do that, we need to verify the 10% condition is met. All right, so A, the mean of the sampling distribution of x bar. Hopefully you remember that the mean of the sampling distribution of x bar is an unbiased estimator, and therefore it should equal the mean for the population, which in this case is 40.125 millimeters. Now, I don't know how many axles this company makes, but it seems reasonable to expect that they can make more than 40 an hour. And if that's the case, the 10% condition is met. We're going to have to assume that that's the case in order to proceed. Therefore, we're going to use the standard deviation formula, sigma over square root of n, and that's 0.001 millimeters. In SRSs of size 4, the sample mean diameter will typically vary by about 0.001 millimeters from the true mean diameter of 40.125 millimeters. All right, you try. The number of absences last year for students at a large high school has a mean of 5.6 days with a standard deviation of 4.1 days. Suppose we take an SRS of 80 of last year's students and calculate the mean number of absences for the members of the sample. So first of all, identify the mean of the sampling distribution of x bar. That value is the mean for the population, 5.6 days. All right, same question, same problem, different question, part B. Calculate and interpret the standard deviation of the sampling distribution of x bar, and of course be sure to verify the 10% condition is met. Oh, and the bar from the x seems to be between the word that and the. It should be on the x. All right, so we don't know exactly how many students are in this high school, but if it's a large high school, we can reasonably assume there are more than 800 students. So we're going to continue. Using the formula, the standard deviation for the sampling distribution of x bar is sigma over square root of n. That works out to be 0.4584 days. And therefore, in SRSs of size 80, the sample mean number of absences will typically vary by about 0.4584 days from the true mean of 5.6 days. The shape of the sampling distribution of x bar depends on the shape of the population distribution. If the population distribution is normal, then so is the sampling distribution of x bar. This is true no matter what the sample size is. And if you think about it, that makes sense. If you have a normal population and you take a sample of size 1 and you take all possible samples of size 1 and plot them, you're going to get a normal distribution back because you're just going to get the whole population. If the population is normally distributed with a mean mu and a standard deviation sigma, then the sampling distribution of x bar will be normal with the same mean, but the standard deviation will be sigma over square root of n, provided that the 10% condition is met. So the larger the sample size, the smaller the standard deviation will be, and therefore you'll still have a normal distribution, but it'll be far narrower. Now, keep in mind, that square root of n in the denominator is important. Many students lose credit on probability calculations involving x bar because they forget to divide the population standard deviation by the square root of n. Remember that averages are less variable than individual observations. If the population distribution is not normal, we need to use something called the central limit theorem. So to understand it, take a look at these populations. The first parent population is uniform. The second one in the middle is skewed to the right, and the third one is two separate groups of data with a large gap in the middle. The second row is the distributions when you take samples of size 2. So these are sampling distributions of samples of size 2. And in the bottom, sampling distributions of samples of size 25. So these images show the approximate sampling distributions for x bar for samples of size n equals 2 and n equals 25 from 3 different non-normal populations. Notice that as the sample sizes increase, the sampling distribution of x bar changes shape. It looks less like that of the population and more like a normal distribution. When n is large enough, and as long as the observations in the sample are independent, the sampling distribution of x bar is very close to normal. And here's what's remarkable. It does not matter what the shape of the population distribution is. And this is the central limit theorem. Draw an SRS of size n from any population with a mean mu and a standard deviation sigma. The central limit theorem says that when n is sufficiently large, the sampling distribution of the sample mean x bar is approximately normal. It's called the central limit theorem because this theorem is so central to statistics. Now you might be asking, how large is sufficiently large? Well, technically it depends on the population distribution. The further from normal the population distribution is, the larger n needs to be in order for the central limit theorem to apply. You'll notice that we're abbreviating central limit theorem CLT. This theorem is used throughout statistics, and this is a standard abbreviation. If you write CLT, statisticians will know what you're talking about. So even when the population distribution is very non-normal, the sampling distribution of x bar often looks approximately normal with sample sizes as small as 25. You saw that in the 3 examples on the previous slide. To be safe, we require that n be at least 30 in order to use the central limit theorem. So if the population distribution is normal, the sampling distribution of x bar will also be normal, no matter what the sample size n is. If the population distribution is not normal, the central limit theorem says that the sampling distribution of x bar will be approximately normal when the sample size is sufficiently large, and we define sufficiently large as n is greater than or equal to 30. If the sample size is small and the population distribution is not normal, the sampling distribution of x bar will retain some characteristics of the population distribution. For example, skewness, and we will not be able to use normal calculations. All right, so here's another example. A bank in a small town has to stock its single automated teller machine, the ATM, with cash at the beginning of each day. Based on thousands of transactions in the past year, they know that the average amount of money requested by a customer is $87, with a standard deviation of $52. The distribution of money requested is strongly skewed to the right. The bank estimates there will be 50 customer requests for cash for the ATM each day, and the bank is trying to decide how much total cash should be stocked in the machine at the beginning of each day. Please calculate the probability that a random sample of 50 customers' requests for cash would require a total of $5,000 or more, or an average request of $100 per customer. And I'm going to pause right here for a moment